Okay, let's unpack this.
The pace of AI innovation is just, it's astonishing. Machine learning, deep learning, generative AI. But here's the core conflict we're seeing.
What's that?
The development is just so rapidly outpacing standardization and, the security architecture we need.
Exactly. And for you, the listener, implementing AI might feel, I don't know, conceptually similar to adopting a new cloud solution. You're moving a critical function.
It feels that way on the surface.
But the sources we looked at are really clear that AI is fundamentally different because it creates these whole new risk vectors. The inputs, the outputs, they're not always predictable.
And that introduces these significant, really complex risks. We're talking data privacy, ethics, and just plain misleading results.
So if we don't establish the right guardrails, and I mean, right now, that attack surface is just going to grow exponentially.
Oh, absolutely. And we won't just see the old vulnerabilities. We're going to see entirely new types of exploits that attack the models themselves, and they'll appear fast.
So our mission in this deep dive is to lay out those necessary guardrails. Everything from the initial design and architecture all the way through to continuous monitoring. To secure the frontier, we first have to map it out.
A good place to start is the architecture itself. Fundamentally, AI isn't just one thing. It's a multidisciplinary field. Computer science, math, even cognitive psychology.
And we can break it down a couple of ways, right? By functionality and then by capability.
That's right. Functionality gives you a scale of complexity. From simple reactive machines up to limited memory systems and beyond. But capability is what it can actually do.
And that's where we get the terms everyone hears about, like ANI.
Exactly. The three tiers. You have artificial narrow intelligence, ANI, which people often call weak AI. Then there's the future stuff, artificial general intelligence, or AGI.
The kind that can perform any intellectual task a human can.
Potentially, yes.
Right.
And then way out there is artificial superintelligence, ASI. But for now, almost everything we interact with, everything impacting business today, falls squarely into that ANI category.
So think predictive analytics, customer service bots, that sort of thing.
Precisely. ANI is incredibly accurate, but it's limited to one specific domain. A great example is an autonomous vehicle. That car isn't one single superbrain.
It's a bunch of different ANI systems working together.
Exactly. You have computer vision, GPS for routing, control systems for the actual driving. They're all highly accurate, narrow scope systems, but they're coordinated.
And that distinction is really important for security. Now let's get into that architectural hierarchy. Where do things like machine learning and Gen AI fit in?
Okay, so AI is the big umbrella term. Under that, you have machine learning, ML. It's the subcategory that builds predictive models directly from input data. It's all about finding patterns.
And deep learning, DL, is a subset of that.
A very powerful subset of ML, yes. This is where we use these multi-layered algorithms, neural networks, to learn really complex hierarchical representations. This is what enables things like sophisticated image classification.
So ML finds patterns. DL uses deep layers to find hidden relationships in those patterns. So where does generative AI come in?
Generative AI is kind of the current peak of deep learning. It's the part that's capable of generating brand new original content, code, text, music, those hyper-realistic images.
Understanding that hierarchy AI, then ML, then DL, then Gen AI, that feels like step one to grasping the new security challenges.
It is. And it brings us right to the core technical risk that the sources all point to, the black box problem.
Right. Why is this lack of explainability such a massive security and, I guess, a liability issue?
Well, what's so fascinating is that these models, especially deep learning models, can become completely opaque. They operate as black boxes.
Meaning you can't trace how a decision was actually made?
Not really.
Yeah.
You can see the input and you see the output, but the journey between them, the weighting applied by billions of mathematical connections, it's practically untraceable.
So the complexity itself becomes the vulnerability. If you can't trace the decision, you can't fully audit it, and you can't guarantee it wasn't biased or, tampered with.
Exactly. That lack of transparency is a critical risk when you're talking about high-stakes applications.
Yeah.
Business-critical, even life-critical decisions.
And with generative models, the risks go beyond transparency. We're talking about really profound legal and ethical problems, especially with intellectual property.
Absolutely. Gen AI is trained on these vast amounts of existing data. It's transformative, but it also creates huge risks around copyright and infringement.
If a model spits out something that looks a lot like copyrighted material it was trained on, who's liable? Who owns it?
Those are the big unresolved legal questions. The sources really stress that organizations have to plan for that ambiguity right now.
We see this power in things like JANs, the general adversarial networks.
Right, the dual network systems.
Hmm.
You have a generator competing against a discriminator. It's how we get hyper-realistic outputs, synthetic images, realistic voices.
Which also raises the bar for deepfakes and fraud.
It does. And just as we're all starting to grapple with Gen AI, the next evolution is already emerging, agentic AI.
These are AI agents that make autonomous decisions to achieve goals, right?
Exactly. Things like optimizing a supply chain without direct human intervention.
That sounds incredibly powerful, but the autonomy part sounds risky.
It is, but what's interesting is that the sources suggest agentic AI is actually less likely to produce those weird hallucinated outputs you see from some Gen AI
Why is that?
because of its improved judgment and more structured problem solving. It's better suited for complex workflows or medical diagnostics, but, and this is a huge caveat, it has to operate with human oversight.
Okay, before we get to the life cycle, let's quickly touch on the 3 basic ML learning paradigms. They really dictate the security you need for the training data.
Right, so first you have supervised learning. It's like teaching a child with flashcards. You use a ton of labeled data to map inputs to outputs.
And the risk there is in the data itself. Garbage in, garbage out.
Or, more dangerously, bias in, bias out. The model will learn and amplify any bias in that training data.
Okay, then there's unsupervised learning.
This is where it learns on its own from raw, unlabeled data. It just detects patterns. Think about anomaly detection in security logs.
And the risk is that it finds something, but you don't know why.
Precisely. The lack of explainability. That means you absolutely need a human-in-the-loop in HITL to validate what it finds.
And the third one is reinforcement learning.
RL. This one learns from consequences, rewards, or penalties. It's perfect for something like an adaptive intrusion detection system. But because it's so autonomous, the real imperative is putting up safety and ethical guardrails so it doesn't explore somewhere it shouldn't.
So the whole journey for an AI system is defined by this AI lifecycle. The sources mention the OECD framework: plan, collect, build, TEVV, deploy, operate, and finally retire.
And it looks a lot like a standard software development lifecycle. But the risks are just. They're unique at every single stage.
How so?
Because AI systems adapt and evolve after they're deployed. A risk that was latent in the design phase might only show up months later after the model gets retrained on new, maybe poisoned, data.
And across all those phases, the one constant dependency is data.
Data acquisition and governance is everything. You need rigorous agreements that identify the data's origin and legal basis. The sources call it provenance.
And you have to have the right consents in place, ones that align with the intended purpose of the processing.
That concept of intended purpose is where a lot of organizations are going to get into trouble.
I can see that. So if a customer gave you consent to use their data for, say, billing.
Right, that consent does not automatically give you permission to reuse that same data to train a new AI model for credit scoring. That requires new governance and most likely new consent.
And that data, even if you try to anonymize it, it's getting harder to say it's not connected to a person.
It is. The sources note how hard it is to disregard claims that data is indirectly connected to people. The sort of digital fingerprint of human activity is everywhere. It means compliance rules like GDPR have a much wider scope now.
With the data being so critical, that brings us to the validation step. TEVV. Testing, evaluation, verification, and validation.
TEVV is about making sure the system is accurate, but also trustworthy and secure. It's how you protect the confidentiality, integrity, and availability of the AI solution. A key method for this is AI red teaming.
So what does that look like in practice? Is it like penetration testing?
It's similar in spirit. It means emulating real-world adversaries to find the model's blind spots. But instead of just looking for code bugs, you're actively trying to trick the model, poison its inputs, and really stress test all the assumptions you made about its safety.
This all sounds rigorous, but then we get to emergency change management. This part of the source material really stood out to me as a massive shift from normal IT.
It's the biggest operational conflict, without a doubt. In conventional software, you find a critical bug, you roll out a hot fix. Maybe it takes a few hours a day or two.
That's the accepted standard, right?
It is. But AI models just don't work that way. An urgent security fix, which usually means retraining a new corrected model, can take hours to weeks.
Weeks!
Weeks. You can't just patch a neural network. You have to retrain huge parts of it. And that takes a ton of time and resources.
So if a critical model is under attack, the fixed timeline is weeks, but the business expectation for a critical incident is hours. That's a fundamental clash.
That is the reality. Organizations have to plan for alternatives. You have to be able to instantly roll back to an older verified model or, and this is key, implement input and output validation outside the model itself.
Like a shield.
Exactly. A shield that can be deployed quickly to protect the model from bad input until that weeks-long fix is ready.
Okay, let's shift to the human side of this. Privacy, ethics, trust, and safety. These are all interwoven, really, around preventing harm.
That focus on demonstrable harm is what's driving a lot of the new laws and compliance frameworks.
And for privacy rights, the AI process has to maintain all the consumer rights we're used to. The right to be informed, right to access, and the big one, the right to be forgotten.
Which loops right back to consent. If an airline wants to use its rewards program data to train a new AI for travel recommendations, it has to make sure the original sign-up covered that. If not, they need new consent.
Ethically, the automatic decision-making is creating entirely new challenges. We're seeing this in things like the EU AI Act, which just flat out classifies some uses as unacceptable.
And that list from the sources gives some really concrete examples of where that line is. Things like AI for social credit scoring, emotion recognition systems at work, or untargeted scraping of facial images. Those are just off limits.
And back to the black box. Trust is fundamentally broken if you can't see how a decision is made. You mentioned a shift in how we think about risk acceptance.
This is a tough one for security professionals.
Mm-hmm.
They're used to documenting known vulnerabilities. But AI, especially deep learning, is inherently experimental.
So what do they do?
Security teams are now being forced to document not just what they know about how a model might fail, but also what is not known about how it works. That documented uncertainty is becoming part of the risk framework.
Moving to safety, which is everything from physical robots to, deep fakes. The core strategy here is human in the loop, HITL.
HITL is the safety net. It's a person who oversees the AI and makes the final critical call. A doctor reviewing an AI diagnosis, a pilot overriding an autopilot.
And that's shifting a bit, right, towards AI in the loop.
A little, yeah. AITL is more about the AI augmenting the human, giving them better insights. But the person is still in control and holds the ultimate responsibility.
Okay, finally, let's look at the architectural controls for this. It all starts with being secure by design.
It has to. Security can't be an afterthought. It has to be woven into the AI development from the very beginning, from inception to end of life.
And in terms of data security architecture, the sources pointed out two really specific, kind of counterintuitive challenges.
Yes. The first is the tokenization issue. A lot of deep learning models need to tokenize raw, sensitive data. That means converting it into a mathematical matrix.
And during that process?
During that process, the data might need to be temporarily decrypted into clear text. It's a fleeting moment, but it's a window of vulnerability.
So your security perimeter is weaker than you thought right there in the development lifecycle.
Exactly, which means you need much stricter access controls at the development layer. And the second challenge is concentration risk.
Because you have to pool all this data together to train the models.
You're aggregating vast amounts of sensitive data into one place, usually a data lake. And that makes that one central location a prime, high-value target for attackers.
So beyond the traditional security, we need continuous monitoring that's tailored for these unique threats.
We have to monitor for hallucinations, where a model just makes things up that sound plausible. We also need to be vigilant against data poisoning,
where a bad actor messes with the training data,
to subtly influence the model's behavior down the line. And then there's maybe the most insidious threat of all, model drift.
That's where the model's performance just degrades over time.
Because the real world changes. The economy, societal norms, anything. The relationships between variables shift. So your monitoring tools have to track performance against a set threshold.
Yeah.
Say accuracy drops below 85%, and that immediately triggers a review or retraining protocol.
We should probably end on a risk that every organization has, shadow IT, or in this case, shadow AI.
Unapproved AI applications. Employees using public domain models for work. It's a huge governance risk. You have proprietary data leaking out into these public systems. Those have to be found, assessed, and either removed or brought under the official security architecture.
So what does this all mean?
The security paradigm for AI is just. It's less about patching software and far more about rigorous data governance. It's about embedding ethical checks throughout the lifecycle and implementing constant real-time monitoring for these unique threats like drift and adversarial attacks.
And the sources are clear that implementing robust access controls and mandating things like input templates for Gen AI are critical first steps to reduce that immediate risk.
But here's the final provocative thought for you to consider. We talked about that fundamental conflict. The time needed for an urgent AI fix is measured in hours to weeks, yet the speed of new threats demands an instant response. Given that chasm, how should your organization calculate its actual tolerance for AI-related operational risk, knowing that the clock is ticking far, far faster than your recovery protocols can handle?